Hello.
Sir, this call is now being recorded. Sir, it's related to liquid flow.
Ah,
It's actually not related to what we are learning, but I needed
hmm.
to do my project, sir. Can you tell
Okay.
me,
Ah,
uh, like, what law or rule governs the, turbulence
hmm.
in a given flowing liquid in a pipe? Like,
Hmm.
at what rate does it lose its kinetic energy? And it is based on what factors? Is there any detailed theory about it?
Which project you are doing? Actually, tell me your title of the project work. Actually.
Sir, it's modified elevator technology.
Ah.
For
Okay, whatever you are having doubts, can you message me so that I'll go through clearly and I'll inform you.
Yes, sir. Okay.
Huh?
Okay.
So what is your project work? So what you are doing? What is your question? What you want exactly like that? Just you message me so that I'll
Okay.
go through and I'll give the clear idea. Hmm?
Yeah.
Okay.
Yeah, I'll message you.
Okay.
Okay. Okay.
Okay, we'll discuss some more problems because problems are most important in ideal gas and real gases. The derivations are much less. Only you have to concentrate on van der Waals constants. Okay, and then molecular weight of real gases, general gas constant for ideal gas mixture. Next, we're having Dalton's law of partial pressure, then Avogadro's law of additive volumes. Anybody know what is the Avogadro's law? Can you tell me? Already studied Avogadro's law. That is also there in ideal gases.
So equal volumes of all gases have equal number of molecules at the same temperature.
Mhm. Equal volume of.
Equal volumes of ideal gases have equal number
Mhm.
of molecules at the same
Mhm.
conditions of pressure and temperature.
Okay, so sometimes they may ask this one also. So just you remember this one also. Avogadro's law. Avogadro's law, Dalton's law of partial pressure, Amagat's law of additive volumes, and one more. We discussed the law of corresponding states. Anybody, can you tell me law of corresponding states related to your real gases already studied? Anyone? Law of corresponding states. Anybody? Because don't forget any concept because they may ask anything in the exam. That's why you should remember.
Or when
Mm,
fluids are
mm,
reduced to the same temperature and pressure,
correct.
then they have the same approximate compressibility factor, and the
Mm,
deviation
mm,
from ideal gas behavior is can be
mm.
compare. I mean, it's comparably the same.
Correct. Okay. So remember, in case of real gases, we are having the formula PV equals to ZRT. Z is PV divided by RT. Z is a compressibility factor which gives the deviation of real gases from ideal gases, and the value of Z varies from 0.22 to zero point 0.3. Okay, and we studied limitations of van der Waals equation. So where in most of the cases the compressibility factor is obtained between zero point 0.2 to zero point 0.3, hence whatever the results obtained are not so accurate in particular reasons. Okay. Um, and Z is function of PR and TR. Okay, so remember compressibility factor mainly depends upon the two parameters. Okay, one is pressure and one is the temperature. We study reduced parameters also. Reduced pressure is actual pressure divided by critical pressure. Uh, Reduced temperature is actual temperature divided by critical temperature, and reduced volume is the actual volume divided by the reduced volume. Okay, when the ideal gas or any gas okay having sorry is related to real gas only. Okay, when the real gas is having the equal or same reduced pressure and temperature, then they should have the reduced volume also. That is the law of corresponding states, and we studied the compressibility factor, compressibility chart, how to solve the numerical problems using the compressibility chart. Okay, so today I'll discuss one more how to find out. We till now we concentrate on ideal gas. Okay, don't make confusion between gas and gas mixture. Okay, in gas mixture, so you are going to find out the individual gas separately. Okay, so I'll do one important problem. Just you concentrate on this one. Okay, such kind of problems only they'll ask in the examination. Okay, so this problem, okay, heading is not there, so I'll give the problem definition as 1 kg of gas, oxygen gas and 2 kg of nitrogen gas in ideal gas mixture having the initial pressure of 150 kilopascal and initial temperature of 293 Kelvin. These are the data given in the problem. Actually, heading is not visible here. That's why I'm giving the explanation for the ideal gas mixture problem. So whatever problem I'm explaining, so one of the important problem. So this kind of question they may ask for 10 marks. Okay, that's why I try to understand this properly. It is very simple problem. Okay, so ideal gas mixture having 1 kg of oxygen gas and 2 kg of nitrogen gas having the initial pressure of 150 kilopascal and initial temperature of 20 degrees Celsius. Okay, 20 degrees Celsius we are converted into 293 Kelvin. So what are the things you are going to calculate? First one, you have to calculate the mass fraction of the individual gas. Second one is the general gas constant for ideal gas mixture. Okay, and third one is you have to find out the specific heat at constant pressure and specific heat at constant volume for ideal gas mixture. Okay, and finally you have to find out the change in entropy of the gas mixture. Okay, these are the things what we are going to find out in this problem. Okay, so already you know the mass fraction of the individual gas is the mass of the individual gas divided by the total mass of the mixture. In the similar way, you have to find out first YO2. YO2 is the mass fraction of oxygen gas. That is equals to the mass of the oxygen gas divided by total mass of the mixture. The mass of the oxygen gas is given as 1 kg divided by the mass of oxygen is 1 plus mass of nitrogen gas is 2. So we are getting the mass fraction as 0.33. Okay. Second one is you have to find out the mass fraction of nitrogen gas. That is the mass of nitrogen divided by the total mass of the mixture. Mass of the nitrogen is 2 kg divided by the total mass of the mixture is 1 plus, that is totally you are getting uh, mass fraction of the nitrogen gas as 0.62. Okay. Next, we have to find out what is the gas constant, general gas constant for oxygen gas and nitrogen gas. That is R bar, that is the universal gas constant divided by molecular weight of the oxygen gas. Already we studied this one relationship between the general gas constant, universal gas constant, and molecular weight. Okay, first, we have to find out the general gas constant for oxygen gas is 8.314 or 8314.3 joules per kg. When you remember this value, the universal gas constant represented by R bar, the standard value for R bar is 8.314 kilojoules per kg Kelvin or 8314.3 joules per kg Kelvin divided by molecular weight of oxygen is 32 because it is O2 16 into 2 32. We are getting the general gas constant for the oxygen gas as 259.2 joules per kg Kelvin. Okay, and then the general gas constant for nitrogen gas is in the same way. You have to find out R bar divided by the molecular weight of nitrogen, that is 8314.3 divided by 28. You are getting 296.94 joules per kg Kelvin. And in the previous class, we derived one derivation, that is the general gas constant for ideal gas mixture is summation of YIRI. Okay, I hope you remember that one. It's very simple. Whatever the mass fraction multiplied by molecular weight of the oxygen gas plus mass fraction of your nitrogen gas multiplied by general gas constant for the nitrogen gas. So by adding this one, you'll get the general gas constant for ideal gas mixture. So here, first you have to find out the general gas constant for individual gas or the constituent gas. Then we have to find out the general gas constant for gas mixture. That is mass fraction multiplied by general gas constant for that particular gas plus in the same way you have to follow, that is 0.33 multiplied by 259.82 plus 0.67 multiplied by 296.94. You'll get 284.7 joules per kg Kelvin. Okay, so when you use this formula, you're getting this one. And in the ideal gas, we assume that 0.287. I hope you remember. So suppose if the values are not given, you are going to assume 0.287. So when you calculate using this formula, we are going to get 284.7 joules per kg Kelvin or 0.284 kilojoules per kg Kelvin. This is the first part. To find out the general gas constant for ideal gas mixture. Uh, okay. Next, we have to find out what is the molecular weight of the gas mixture. Okay. Once again, you apply the same formula. R equals to R bar by M. Okay. So what I am explaining is related to gas mixture. You remember, till now we studied only ideal gas, taking the entire gas. Now here we are studying on the constituent part. R equals to R bar divided by M. So molecular weight equals to R bar divided by R. So R bar is always 8314.3 divided by R is 284.7. So molecular weight of the ideal gas mixture is 29.2. Okay. Next, we have to find out the CV value. Okay. They are given it as 7 by 2 R. Anybody can explain how you are getting the 7 by 2? Anyone can imagine the specific heat at constant pressure is 7 by 2 R they are given. How you are getting 7 by 2? Anyone can you tell me? Cp equals to 7 by 2 R they are given. Okay, how will you get 7 by 2 R? Okay, hope you understood the formula R equals to Cp minus of Cv. Remember that formula?
Yes, sir.
Okay. R equals to Cp minus Cv. And here we don't know Cp, we don't know Cv. Only we know the value of R. That is what you are going to do. You have to divide throughout equation by Cv. So Cp divided by Cv minus of Cv divided by Cv equals to R divided by Cv. Like that you have to concentrate. Okay. Because some of the things you should remember. Once you understand the concept, then only you can proceed the problem. Suppose if you stuck in between, you are not able to proceed at all. That's why I'm telling you, try to understand the basic concepts, most important. Okay, so suppose you're not able to remember that formula, because in this case we are going to find out the two values, Cp and Cv. Only the value we know R. Then you have to think that what is the relationship between Cp, Cv, and R. So we have to think of, okay, R equals to Cp minus Cv, dividing throughout by Cv, that is we'll get R divided by Cv equals to gamma minus 1, or Cv equals to R divided by gamma minus 1. And one more thing I'm telling you, gamma you have to assume that is 1.4, because we are dealing with ideal gas, and the gamma adiabatic index for air is always it is 1.4. Using that formula you can find out first Cv. Cv equals to R divided by gamma minus 1. Okay, Cv equals to R divided by gamma minus 1. Using that formula, already we know the value of R. That is, you have to take the gas constant for the mixture, that is 29.2, divided by comma minus 1. Okay, you'll get the CV value as 71.75. Okay, so you check it out, just you confirm whether you're getting this answer or not, because this problem what I am explaining now, it is the most important problem, very simple problem. So but it is the most important problem. Next, you have to find out the value of CP. Okay, so in that case, what you are going to do? CP already once we know CV, we can find out the CP value easily, because CP by CV equals to 1.4. So CP is 1.4 times that of CV. That also you can do it. Okay, suppose you are not understanding this formula, better you go for that one. CP by CV is 1.4. So is always 1.4 times greater than that of CV. You'll get around 996.45. So this is the most important to find out the specific heat at constant pressure and specific heat at constant volume. Okay. And here, this process, sometimes they may ask to find out the change in entropy. Okay, the change in entropy, already I derived the derivation for the change in entropy for constant volume. So whatever process it is there, no, it is constant volume actually. Sometimes they make you the constant pressure also. Okay, so what is the standard equation for your entropy change for constant volume process? MCV into ln T2 by T1. Anyhow, this term is neglected because V1 and V2 is same. Just you remember MCV ln into T2 by T1. This is a change in entropy for the constant volume process. Can you anybody tell me what is the change in entropy for adiabatic process? What is the change in entropy for adiabatic process? This module 5 is the combination of second, third, and fourth module. Okay, that's why don't forget the basic concept. Can you tell me what is the change in entropy for adiabatic process? Delta S for adiabatic.
Zero.
Zero. Good. Okay. How about constant pressure process? What is the formula?
Sir, P V2 minus V1. I mean, sorry, that's the work done. So we calculate the changes in heat and we
Mm.
divide it by the change in temperature.
Mm.
One second. I'll tell the exact formula.
Yeah, yeah, I want exact formula.
One second. Sir. So for constant volume process,
Mm.
constant pressure process, right?
Yes.
Yeah, it's MCP ln T2 by T1.
Okay, good. Okay, for like that, you should remember for constant volume, just you take MCV and T2 by T1. For constant pressure, instead of CV, you should take CP. That's why you have to understand like that. And the for adiabatic process, change in entropy is always zero. How you are getting entropy is zero means just you have to analyze the Clausius theorem. That Clausius theorem is what? ds equals to dq by t, right?
T2 by D. Yeah.
So adiabatic
Zero.
process, dq is always zero. So
So
ds
ds
is
equal to
zero, and you have to integrate. You'll get the s as constant, and based upon that one, you have to draw the ts diagram. You get the vertical straight line in case of ts diagram. That's why if only one you have to understand the basic principle. Once you understand the basic principle, you can do anything. Okay, so you can draw pv diagram, you can draw 3s diagram. So you have to write the formula, everything. Okay, that's why I said you have to remember the PV diagram and TS diagram for 5 process, and then these are the 5 parameters. You remember what is the work done during the constant volume process and all other process. Second one is the change in internal energy, and then third one is change in enthalpy. Fourth one is the amount of heat transferred during a particular process, and finally the change in entropy. So this 5 into 5, that is 25 things you should remember, plus 10 PV diagrams, sorry, 5 plus 5 PV diagrams and TS diagrams. So you should keep all the things in the mind. You can easily do any number of the problem, any sort of the problem. Okay, that's why you practice well, and just you remember the basic things. Okay, next, by substituting the value, we get the delta S as 515 joules per Kelvin. Okay, 0.515 kilojoules per Kelvin. Okay. Now you see how they are asking the question in case of VT. Okay, write down the van der Waals equation of state. How it is different from ideal gas equation? Explain the law of corresponding states. So obtain the expression for conditions of A and B and R in terms of critical properties for a Van der Waals gas. Okay, like that they will ask. This is for 20 marks question. So for each question we are having 3 bits. Okay, so they ask like this. Okay, law of corresponding states. So you have to explain for 4 marks, and this is for 8 marks, and a derivation for 12 marks. Okay, that's why whatever the concepts are said, all are important. You see, you have to explain or write short notes on reduced properties, compressibility factor, law of corresponding states, generalized compressibility chart. Okay, so it is 2 into 4, that is 8 marks, and in this case, you don't write too much. You have to explain very briefly. So suppose you are explaining half page or one page, you'll not get the time to solve the other questions. That's why first you see the marks. You see, 8 marks for 4. Okay, means each question carry 2 marks. You have to write around 3 to 4 lines enough. Okay, and here write down the Van der Waals equation of state. In what ways it is improvement over the ideal gas equation. So here just you write the Van der Waals equation and how you are getting the A and B constant, how you are getting the A and B. You have to explain everything. We are obtaining the constants A and B in terms of reduced parameters. Like that, you have to explain how it is different from ideal gas equation. Okay, based upon the marks, you have to do the problem. Okay, so I'll do one more problem. The heading is not visible, so I'll explain the problem. This question asks for uh, 4 marks. Okay. So they are given 6 kilomoles of hydrogen and then 4 kilomoles of nitrogen in an ideal gas mixture. Our aim is to find out the mass fraction and general gas constant for the mixture. In the previous problem, what we studied, they are given in terms of kilogram, but in this problem, they are given 6 kilomole of the hydrogen and 4 kilomoles of nitrogen. Don't take this kilomoles and don't club with the moles and kilogram. They are all different. Okay, first step is we have to convert kilomoles into kilogram. So what you are going to do, just you are going to multiply by the molecular weight of that particular gas. Okay, 6 kilomole of hydrogen is nothing but 6 whatever given in the problem multiply by molecular weight of hydrogen. We get 12 kg, and then 4 kilomoles of nitrogen. Okay, that is 4 into 20. Okay, 112 kg. Suppose if you are putting 6 and 4, it is wrong. I am telling you. Only you have to convert the kilomoles into kilogram. That is important. First, you are going to multiply by the molecular weight of the gas. So we are getting the mass of hydrogen gas is 12 kg and the mass of nitrogen gas is 112 kg. Next step is we have to find out the mass fraction of hydrogen gas. Mass fraction of hydrogen gas is 12 divided by total mass of the mixture. 12 plus 112. We are getting 0.09068 divided by y into, that is 112 divided by 12 plus 112. So we are getting 0.902. As I said, you should remember this is a general gas constant equation for ideal gas mixture, that is summation of yi into r. Yi is our mass fraction. First you have to take mass fraction 0.0968 multiply by the general gas constant for hydrogen gas plus 9038, that is mass fraction of nitrogen gas multiplied by the general gas constant for nitrogen gas. 0.0968 multiplied by same thing, that is r bar divided by M. Okay, so R bar is 8314.3. You should remember this value. Molecular weight of hydrogen is 2. So 0.9032, it is the mass fraction of nitrogen gas multiplied by 8314.3 divided by molecular weight of nitrogen. So after solving this one, we are getting the value of gas mixture as 670.6 joules per kg. So now I'll do one problem. It includes the entire thing. Okay, it's a very big problem. So try to understand. Once you understand the basic concept, easily we can do this problem. Okay, so a lot of things, all the things are included in this problem. Okay, we'll see. First, you'll see the um, explanation for this problem. Okay, a mixture of ideal gas consisting of 2.5 kg of nitrogen and 4.5 kg of carbon dioxide at a pressure of 4 bar and temperature of 25 degrees Celsius. Two values are given. Okay, 2.5 kg of nitrogen and 4.5 kg of carbon dioxide at a pressure of 4 bar and temperature of 25 degrees Celsius. Okay, determine the mole fraction of each constituent. Okay, so here in the previous problem we studied mass fraction. Here we are going to study the mole fraction. Okay, then second one, molecular weight of the mixture. Okay, what is the molecular weight of the mixture? The gas constant for the mixture, the partial pressures and partial volumes, the volume and density of the mixture, the Cp and Cv of the mixture. Okay, if the mixture is heated at constant volume, you see it is a constant volume process at temperature 35 degrees Celsius. Okay, what will be the change in internal energy, change in enthalpy, and change in entropy of the mixture, and also determine the changes in the same properties when the heating is done at constant pressure. Okay. So first you concentrate on constant volume, so then we have to do it on constant pressure. You see, the one problem which includes everything. Okay, everything they have asked in single problem. Okay, and they are given take gamma equals to 1.285 for carbon dioxide gas and gamma equals to 1.4 for nitrogen. So whenever they are giving in the problem, directly you have to take these values. Otherwise, you have to assume okay, gamma is 1.4 for air. But in this problem, they are given clearly. Gamma is 1.285 and gamma is 1.4 for nitrogen. So first part we have to do first after reading this one, you have to write the given data. That is mass of oxygen is 2.5 kg, mass of nitrogen is 2.5 kg, mass of carbon dioxide gas is 4.5 kg. Okay, pressure is 4 bar and temperature is 25 degrees Celsius and it is a constant volume process. The first part is we have to find out the molar fraction. Mole fraction. Can anybody tell what how we define the mole fraction? What is the
So
definition?
mole fraction is the number of moles of a given substance per total number of moles of the mixture.
Okay, but in this
The number
problem,
of,
they are given kg. How we are going to convert into moles? Can anybody tell me?
so we divide it by molecular weight.
How much you'll get for nitrogen and how much you'll get for carbon dioxide?
So for nitrogen it's 28, and for carbon dioxide it is 44. So
Mm. Mm.
we can
Yeah, good answer. Okay,
divide
so
them.
Correct. Good. Okay. So whenever you are going to convert kg to kilomoles, you have to divide by molecular weight. Okay. Whenever you are going to convert kilomoles into kg, you have to multiply by molecular weight. Keep in mind. Okay. So in the previous problem, we solved kilomoles to kilogram, but here it is reverse. We have to convert kilogram into kilomoles. You have to divide by the molecular weight. Our aim is to find out mole fraction of the each constituent. According to the definition, mole fraction is nothing but the number of moles of individual gas divided by total number of the moles of gas mixture. Okay. First, we have to find out the kilomoles of nitrogen. That is 2.5 divided by 28. Okay, it's the first step. Don't take 2.5 directly. Suppose you are taking 2.5, that is wrong. Okay, so whenever they ask mole fraction, we have to convert the kilogram into the kilomoles. That is 2.5 divided by 28.0892 uh, mole fraction of nitrogen gas. Similarly, we have to find out the mole fraction of nitrogen is this one. Okay. And total number of next you have to find out the mole fraction of carbon dioxide gas as 4.5 divided by 44. Okay, and then the total number of the moles is okay what you are getting 2.5 divided by 28, 4.5 divided by 48. So what it is nothing but the total number of the moles in ideal gas mixture. Okay, so according to the definition, the mole fraction of nitrogen gas is number of the moles for nitrogen gas divided by total number of the moles of gas mixture. That is 0.0892 divided by 0.1915. So you get 0.4657 is the mole fraction of nitrogen gas. Okay, next we have to find out the mole fraction of the nitrogen gas. That is the number of the moles of carbon dioxide gas you have to find out. That is number of the moles for carbon dioxide gas is 4.5 whatever given divided by 44. Okay, so this is the mole fraction of carbon dioxide gas. Then we have to find out the mole fraction of carbon dioxide gas is the number of the moles for a carbon dioxide gas divided by total number of the moles of ideal gas mixture. Okay, that is 0.10227. This is the number of moles of carbon dioxide gas divided by this molecular weight. So this is the number of the moles of carbon dioxide gas divided by total number of the moles of gas mixture. That is 0.10227 divided by 0.191. So you get the mm, molar fraction of carbon dioxide gas is 0.534. Okay. Next, we have to find out the molecular weight of the gas mixture. Okay, using this formula, we have to find out. Okay, molecular weight of the gas mixture is mu1 m1 plus mu2 m2. So mu1 is the molar fraction of nitrogen gas multiplied by the molecular weight of nitrogen gas plus the molar fraction of carbon dioxide gas multiplied by the molecular weight of carbon dioxide gas. 0.4657 is the molar fraction of nitrogen gas multiplied by 28 plus 0.534, that is the molar fraction of carbon dioxide gas multiplied by 44. Just you do this one, you get 46.535, but unit is most important. Okay, so whenever you are doing with respect to molecular mass, we have to write kg per kg mole. Okay. Otherwise, you have to write in terms of kg. Next, we have to find out the equivalent gas mixture. Okay. Equivalent gas mixture is, as I said, it is summation of yi into ri. So you have to find out mass fraction of the individual gas and the general gas constant for individual gas. Then after that, you have to sum up. You'll get the uh, equivalent gas mixture. Okay. So using that one, we are going to get is m into r into plus m CO2 into r CO2. Otherwise, you do separately, you can do it. Okay, but you should remember the formula summation of yi ri. Summation of yi means first one is y into multiply by r into plus YCO2 multiplied by RCO2. So using that formula, we are going to get the general gas constant for the mixture as 0.2275. So try to understand. They may ask all the things in one problem itself, or they may ask very a particular part. So here in this problem, they ask everything. So we have to find out each and everything or the mixture. Okay, first we found out the molecular, that is gas constant mixture in terms of moles. Then we found out the general gas constant in terms of kilojoules per kg kelvin. And third part is the partial, uh, equivalent gas constant over partial pressure and partial volume. Anybody how to do partial pressure and partial volume? How to find out the partial pressure and partial volume of the gas mixture? Anybody? Hello. 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 Okay. ಹೌದಾ ಹೌದಾ ಯಾರಮ್ಮ ಹೌದಾ ನಾನು ನೋಡಿಲ್ಲ ಮನಿ ಹೆಂಗೆ ಅಂತ ಕೇಳಿದೆ. ಅಲ್ಲ ಇದು ಬಂದಿದ್ರು ಬಹಳ ದಿನ ಆಯ್ತು, 2 3 ವರ್ಷ ಆಯ್ತು ಹಾ 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 ಮತ್ತೆ ಹಚ್ತೀನಿ ಮಾಮ, ದರ್ಗಾಸ್ ಬಿಟ್ಟು ಹಚ್ತೀನಿ ಅಂತ ನಾನೇ. Hello, anybody think what is the partial pressure and partial volume? Anyone? Okay. So partial pressure is given by, you see, uh, partial pressure for nitrogen is molar uh, fraction of nitrogen gas multiplied by the total pressure. Total pressure is given in the problem as 4 bar. That is 0.4657 into 4. You get 1.862 bar. And partial pressure of carbon dioxide gas is the mole fraction of carbon dioxide gas multiplied by the total pressure. Just you multiply by total pressure, you get a partial pressure of the individual gas. Okay. So you are getting 0.4657 multiplied by 4. You get 1.862 bar. And then for partial pressure of carbon dioxide gas is 2.136 bar. Okay. Next, we have to write the ideal gas equation. Can be written as PV equals to MRT for N2. That is, we have to find out the partial volume. What equation we are using is the partial volume. Same equation you have to use. B N2 equals to MRT divided by P. So M is mass of the gas, nitrogen 2.5, and R is 8.314 into 10 to the power of 3 divided by 28 molecular weight of nitrogen multiplied by temperature. Temperature you have to convert in Kelvin divided by 4 into 10 to the power of 5. Okay, don't put P pressure in bar. You have to convert in the Newton meters. But same equation what we are using, don't change the equation. PV equals to MRT. This is the ideal gas equation. Then we are getting the partial volume as 0.553 meter cube for the nitrogen gas. Similarly, we have to calculate for carbon dioxide gas. Carbon dioxide gas is MRT divided by P for carbon dioxide. Same equation you use. Okay, just instead of this mass only changes here. Remaining all the parameters are same. No change in the R also changes. R is R bar divided by M, and remaining parameter is same. Okay, here you have to take The M as 4.5 kg, R is R bar by M into 25 plus 273 divided by 4 into 10 to the power 5. So you get the VCO2 equals to 0.6334. Then volume of the mixture. Okay, here it is most important. You have to take the what is the gas constant mixture. Okay, gas constant mixture is we found out. Okay, a gas constant mixture is that is 0.2275 is there. Okay, now you have to take that 0.275. Okay, so that is 0.22975 kilo. You convert in joules, that is into 10 to the power of 3 into 298, that is 25 plus 273 divided by 4 bar. You get the volume of the mixture is 1.188, but this is what we found out. This is the volume of individual gas. Next, density of the mixture is just mass by volume. Mass is 7 divided by 1.188. How it is 7? Anybody? How it is 7? How it is 7? So just try to understand. It is very simple. This one, okay, chapter. We are not having any complicated formula here. You have to remember the simple formula. Okay. Anybody? How you are getting 7? Mass of the mixture is 7 because you have to take the mass of nitrogen plus mass of your carbon dioxide, that is 4.5 plus 2.5, that is 7, and volume is 1.188. You are getting the density of the mixture as 5.982. Okay, similarly, how I explained, you have to find out the value of the mixture. Okay, CV equals to R divided by gamma minus 1. Just now I said in the previous problem, same you have to find out. So that is 8.3114 divided by 28 into 1.4 minus 1. That is R equals to R bar divided by molecular weight. Okay. So CV, CP, gamma, you have to find out. Okay. Next, I'll explain how to find out the change in internal energy. Change in internal energy is, as I said, any things, any for process, be MCV into delta T. MCV is total mass you have to take. 7 into CV is 0.69, and what you got into 35 minus 25. So you get 48.37. And change in enthalpy for any process, it is given by MCP into T2 minus T1. These two formulas you should remember. Okay, same formula we are using in module 2, module 3. You are getting change in enthalpy as 64.26, and the change in entropy as S2 minus S1, that is MCV into ln T2 by T1. Once again, it is a constant pressure, volume process. If it is constant pressure, you have to use MCP into ln T2 by T1. So these are the things you have to remember. Now tell
Sir,
me.
if we leave the meeting in between by mistake, does it not consider the attendance?
No problem. You enter in the chat box, okay?
Because I have entered, sir, but I'm seeing my attendance
Uh,
is pretty lower than what it should be, sir, in the
okay, okay.
change.
How much? How much?
It's
So
85,
sometime.
sir, but it should be 90, sir. I didn't, like, I
Uh-huh.
think
Uh-huh.
I was absent for only maximum 2 or 3 classes.
Okay, okay, okay. So in that case, what happens? No, suppose you are not entering your USN in the chat box, no, will not consider. That's why don't worry about the attendance. Okay, we'll consider. Okay. So
Yeah,
no, what are the dates you missed and what are the dates you didn't get? No, just you forward me the message which date you attended, how much you want
yeah,
to
yeah.
get. So I'll consider.
Okay.
Okay. Hmm?
Yeah,
Yeah,
okay, sir.
regarding attendance part, you don't worry at all. Okay. Suppose you are attended, no problem.
Yeah,
But don't forget to write in the chat box because I am going to check only in the chat box. Okay.
yeah, okay, sir.
Suppose sometimes you forget the writing the attendance in the chat box. No, please message me. Okay, so that I'll consider.
Yeah, okay, sir. I'll do that.
Okay.
Yeah.
Okay, hope you understood the problem. Any doubts in this problem?
No, sir. No doubt.
Good. Okay. So we will do some more concept in Monday's class. Okay. Now I'll stop the session now. Okay. All of you finished your assignments. I have given two assignments. Okay. Uh, those who have not done the assignment, please complete it and submit in the Google Classroom, because assignment carry marks. Okay, that's why I'm telling you. So suppose you're
Okay,
not
sir.
able, you're not submitting the assignment, simply lose the mark. Okay, submit two assignments. Okay, I gave some simple problems. Just okay, analyze and do it.
Okay, sir.
Thank you for joining the meeting.
Okay, sir. Thank you.